how we can use them to determine a quantitative description of pressure, and also how pressure depends on temperature. We'll talk a little bit about how molecules have distributions of speeds that depend on the mass of the particles, and it depends on the temperature of the system as well. And we'll talk a little bit about collisions between the molecules and the walls, and the frequency in which those collisions take place, and also the average distance that molecules are going to travel between collisions. That property is known as the mean free path. It's the distance, average distance a molecule travels before it collides with another molecule. It gets the symbol lambda. And the assumption here basically is that lambda is a lot greater than the diameter d of the molecule that we're interested in. So these assumptions are going to lead to pressure, speed distributions, and collisions, and ultimately we're going to be able to reproduce the perfect gas law. We'll be able to derive the perfect gas law effectively from these three simple assumptions and follow them through the logical conclusions. So let's talk about pressure first. How is pressure related to molecules? Well, pressure is force exerted per unit area. And it's going to have units in newtons per square meter, newtons being the unit of force, square meters being my unit of area, which is also a Pascal, the SI unit. Well, molecules exert pressure on the walls of a container by colliding with the walls of a container. They're bouncing around randomly. Every so often a molecule is going to hit the surface, and if it hits the surface, it bounces off the surface. And it bounces off the surface elastically. That is, it bounces off with the same kinetic energy as it came in. Alright? So, the molecule, because its velocity changes, or its speed changes as a result of that collision, before the collision it's heading in one direction, after the collision it's heading in the opposite direction, its momentum changes, right? So the definition of a force is the rate of change of momentum, which is mass times velocity. Mass in kilograms and velocity in meters per second. So if we think about how much force does a given molecule exert on a wall when it undergoes a collision, well, it depends on how fast it's moving. It depends on its mass. It depends on its momentum. So if we look at the picture here, you can see a molecule coming in, approaching this wall. We're going to consider this in one dimension to start with. It's heading along this x direction, as we'll call it, with a certain momentum m, and a component of its total velocity along that x direction of vx. Okay, so there's a component of its total momentum along the x direction. Yeah. And velocity is a vector. Its momentum is also going to be a vector. There's a component of the momentum along the positive x direction. So it has momentum m times vx. Okay, that's the component of the momentum along the x direction. It collides with the wall, and then it's turned around. It bounces off the wall. And after the collision, its momentum is minus v m times vx. That is, it's going at the same speed, but in the opposite direction. So its momentum is changed by an amount twice its initial incoming momentum. It's going positive direction, and it's coming out with negative component of velocity. So the change in the momentum is twice the mass times the initial velocity along this x direction. So if this happens in a given unit of time t, well, the force that's been applied is 2 times the mass times the component of the velocity along the positive x direction divided by this delta t, the time in which the collision occurred. So again, m here is the mass of my particle, of my molecule, which we're going to measure in kilograms, and vx is the x component of the velocity. In meters per second. The components along the y and the z direction are going to be completely unchanged by this collision. We'll think about just the component along x, right? So they are whatever they were after the before the collision. They will remain exactly the same. So if we know the mass and we know velocity, we can calculate forces applied to a collision. Well, our sample of gas doesn't just contain one molecule, it contains many molecules. And if we want to know the total force that's applied on average over a certain time interval, we need to know how many collisions there are going to be between the particles that are in the gas and the wall within that same time interval. So we want to calculate the number of collisions in the interval delta t, the same time interval that we're going to be concerned with. How many of those are there? Well, it depends on a couple of things. It depends on how many molecules you have present in general, the number density of the molecules that are present in the gas. It depends on how many of them are close enough to actually reach the wall within a certain time interval delta t, based on the speed that they're moving at. And then there's one other subtle factor that we also have to include a little bit afterwards. So let's start with this picture at the bottom left of the screen. If we imagine some kind of box that is some distance from the wall, which is an area A. Right? This is the area with which the molecules are going to be colliding ultimately. Well, for a given speed Vx, or a different component of the speed Vx along the direction that is traveling directly towards the wall, any molecule that is within a distance Vx times delta t will have a chance of reaching the wall, right? If you're further away than that distance, then for a given speed, it's just not going to make it. Right? So v times x here, this is a distance. It's a speed multiplied by a time interval. So that's the distance from the wall. We can measure that in meters. The particle here is within that distance. If it's going at a speed Vx, it will hit the wall within the time interval. This molecule is a little bit further away. It will travel the same distance in the same time interval, but it's not going to travel far enough to reach the wall. So the only volume that we need to consider ourselves with containing molecules that are going to reach the wall is the volume contained within this box, defined by a distance, Vx times delta t, and the area of the wall. So we can calculate, in general then, a given area here, which will be in meters squared, and the overall volume of this box will be in meters cubed. We've got a volume here, and only those molecules within that volume are going to be able to reach the wall. And that's what this central factor here is. It's A times Vx times delta t. So the volume of space that's close enough to the wall, the molecules with a speed Vx have a chance to reach the wall within this given time interval. How many collisions will there be? Well, it depends on how many molecules exist in that volume. And so we need to know how many molecules there are per unit volume. And that's a property known as the number density, which is effectively a concentration of molecules in a gas. Right? We normally measure concentrations in solution in moles per liter. It's an amount of substance per unit volume. When we're talking about gases, we tend to talk about the number of molecules per unit volume. It amounts to the same thing, amount of substance per unit volume. The number density is given by this term, first of all. Here, it's the number of moles of molecules, M, the amount of substance. V is a volume, again measured in meters cubed. And NA is Avogadro's number, which is units per mole. How can we calculate the number of molecules per unit volume? Well, the best way to start with that is to use the ideal gas law and say that the number of moles of substance per unit volume is equal to P, the pressure divided by R, the gas constant multiplied by the temperature. And that's going to give me a concentration in moles per cubic meter. N over V, moles per cubic meter. If I multiply throughout by Avogadro's number, N times Na divided by the volume is going to be equal to the pressure times Avogadro's number divided by the gas constant times the temperature. We can do a little bit more rearrangement here and say that R is also going to be equal to the Boltzmann constant times Avogadro's number. We'll drop that in a little bit later. We can calculate this and quantify these numbers a little bit more precisely. But this first term is the number density. So, we can calculate that based on the ideal gas law. Yeah.
Is all the probability that a certain amount of molecules will be, a certain amount of moles of something to be in a certain area, is that what that is?
That's the concentration of molecules, right? So this volume tells us about the volume we need to worry about, chances of molecules reaching the wall. The number density is the number of molecules per unit volume, which tells you how many there are likely to be within that volume. Okay, so if we multiply those two together, we're basically figuring out how many collisions there will be within this time interval, delta t. Right? The last factor there is a half, and the half is there for a simple reason. For every molecule heading towards the wall in this volume, there's another molecule that's heading away from the wall, right? There's no preference for travel in the positive x direction versus the negative x direction. So within this volume, half are heading towards the wall, half are inevitably heading away from the wall as well. And the ones that are heading away from the wall are obviously never going to collide with these segments. Okay, so we've got these three different factors. So this one, half travel towards the wall. So the total force applied is the force per collision multiplied by the total number of collisions, which is given by this collection of things here. So F total is going to be equal to N times NA divided by 2B times A times B X times delta T times the force per collision, which is in the equation at the top, which is 2 times the mass times Vx again divided by delta T. So I'm just taking the product here of this stuff with all of this stuff to calculate the total force. Number of molecules, number of collisions multiplied by the force per collision. And we can start to tidy this equation up a little bit. A bunch of things are going to cancel out here. I've got a 2 here and another 2 down here. I've got a delta T here and delta T here. That goes away. If I make another slight change and note that the mass in kilograms multiplied by Avogadro's number is the molar mass, which we will represent in kilograms per mole, then I can unite NA here, this mass out here. Everything at this point is going to cancel out and simplify down. And we have a pretty straightforward expression that says that the force total is applied in this time interval delta T is the number of moles of gas that we have present, the molar mass multiplied by the molar mass of the gas times the x component of the speed squared times the area divided by the total volume. And since the pressure is force divided by area, then the total pressure in my system is this equation divided by A, which just cancels out this factor of A at the end. And so my expression for the pressure is now pretty straightforward. Number of moles of gas times the molar mass in kilograms per mole times the speed squared divided by the volume. That is, the pressure is ultimately going to be proportional to the square of this x component of the speed of the volume. Yeah.
So earlier we said that A, Vx, delta T, we said that that's volume, right?
Yes, the volume of this box.
So are we able, like, in that first S total equation you wrote, that 2B in the denominator, are we able to cancel that with the AVX delta T term next to it?
Cancel the volume.